Hey everyone, and welcome back to Science for Everyone with Tom Copeland. I'm Tom Copeland. Let's get down to science. So we are talking about how to calculate the half-life of an isotope, and by now you should know what an isotope is. An isotope is an atom. It's a different version of the same element. It just has usually extra neutrons, and what happens is these extra neutrons make the nucleus unstable, and that unstable nucleus becomes radioactive. So the atom is trying to become stable and have a stable nucleus again, so it's going to emit radiation. So that may be energy, that could also be particles like a helium atom, electrons. We are not going to talk about the different types of radiation today, but in a future video we will. The important thing though, you start with the parent isotope, it undergoes radioactive decay, and it becomes a daughter isotope. And a lot of times that daughter isotope is a different element because a lot of times you lose helium atoms from the radioactive atom. And so a lot of times you end up with a different atom that most of the time is still radioactive. But we are not really going to get into the types of nuclear radiation right now, and nuclear decay. We're going to focus on how to calculate the half-life of an isotope. So first you need to know, what is an isotope? Blah, blah, blah. No, what is a half-life? We know what an isotope is, people. What is a half-life? So the half-life is the time it takes for half of the isotope sample to decay to more stable matter. This process is random for each individual atom, but a set time of decay can be calculated for a whole sample. Remember that the matter doesn't disappear, it just decays into something else. So I think that's sometimes a common misconception with half-lives, is that stuff is disappearing. It's not disappearing. You still have the same amount of matter you started with, but it's decayed into a daughter isotope and particles. And if you were able to gather all of those particles and atoms, you would still have 100 grams of matter. So real quick, there are some uses for isotopes. You've probably heard of carbon-14, which is used in radioactive carbon dating. If it's an item that's made out of carbon, like bone, like a mummy or a mammoth, or it could be a piece of leather or even a campfire. And carbon-14 is good for about 60,000 years or so. And then after that, there's not enough carbon-14 to measure. But like I said, there's other uses for these radioactive isotopes in research and treating cancer. So there is definitely value in learning about isotopes. Okay, so let's talk more about the half-life of an isotope. It does not matter what isotope we're talking about. It does not matter how much the starting amount is. Every isotope is going to follow this pattern. That's why it's called a half-life. So again, the half-life is the time it takes for half of your original sample to decay into a daughter isotope. So if we look at this chart, this is CO60, so cobalt 60 is a radioactive isotope of cobalt. And you start with 10 grams. After the first half-life, you have 5 grams, then 2.5, then 1.25, then 0.625. And if you notice down on the bottom of this chart, one half-life is 5.27 years. So if you want to know how many half-lives have passed from 10 grams to 0.625, you would just count the half-lives and multiply, in this case, by 5.27. Okay, here's another example of carbon, and if you notice, that J curve is very similar. All half-lives are going to have this same curve. You always start out with a certain amount, and the half-life is different for every isotope, but the definition is the same. The half-life is the time it takes for half of that radioactive isotope sample to undergo decay. So again, those times are different, but the pattern is the same. So if we look at this diagram again, we start with a parent isotope. This is your original sample. after one half-life, you have half of your sample is now decayed into the daughter isotope, and half of your sample is still the parent isotope. After two half-lives, you only have a fourth of your parent isotope left, and the rest of your sample has decayed into the daughter product. So, right, every half-life is half of the amount you had in the previous half-life. So if we were to go to three half-lives, we would only have 1/8 of the original sample left. And this is important too, even though I said it, the matter is not disappearing. As the parent isotope is decreasing, the daughter isotope is increasing. So in the end, we always have the same amount of matter, it's just the nuclear decay is occurring. So I don't want you to think that the parent isotope that matter is disappearing. It's just decaying into particles and the daughter isotope. There is an equation to figure out a lot of missing values with half-life. I'm not going to focus on this equation, especially for high school chemistry. This equation is not given in your reference table, so we're not going to focus on it. But there is an equation if you wanted to research it. But I'm going to show you some other ways to figure out some half-life problems without this equation. So this is what you do. It doesn't matter what your numbers are. It doesn't matter what the amount of time has passed, the time for the half-life. Every problem follows the same general pattern. You start with the original amount and you keep dividing by 2 based off of how many half-lives have happened. And then this pattern is really important. It doesn't matter what your original amount is. You can assume that that original amount is 1. So these blue arrows are symbols for a half-life. Every time you see a half-life, every time you see a blue arrow, a half-life has occurred. So after one half-life, you start with an amount of 1, and you have half of the sample has not decayed. Second half-life is a 4th, third is an 1/8, fourth is a 16th, fifth is a 1/32. We could keep going, but a lot of times with half-lives, the amount left is so small at that point, it's really hard to measure. So we could also do this with percentages. So you start out with 100%, then the first half-life you get 50%, then 25%, then 12.5%, then 6.25%, then 3.125%. But then again, like I said, after about 5 or 6, 7 half-lives, it's really difficult to detect a lot of these radioactive isotopes. So let's go ahead and look at these diagrams real quick, and then we're going to do a couple example problems. So let's say you start with 544 grams of your radioactive isotope. After one half-life, you have 272. Second half-life is half of 272, so you'd have 136. And it keeps splitting in half until you get to how many half-lives you are trying to measure. So after 5 half-lives, we would only have 17 grams of our substance left. Or if this was in atoms, if we started out with 544 atoms, we would only have 17 atoms left. This chart on the left, very similar. You start out with 100, then 50, then 25, 12.5, 6.25. So let's look at 2 example problems. Gold 198 has a half-life of 2.7 days. How much of a 96-gram sample of gold 198 will be left after 8.1 days? The first thing I like to do is write out all of my givens or my knowns. So if we look here, this is something that people get confused with. Gold 198, that's its isotopic notation. That's the name for that isotope. You are not going to be doing anything with the 198. The gold 198 is its name, so do not get confused and think you have to use that in your calculations. We also were given the half-life, which is 2.7 days. We were given the starting amount, which is 96 grams, and the amount of time that has passed, which is 8.1 days. So if we use our givens, the first thing I would do, I know that the half-life is 2.7 days. I know that 8.1 days has passed. So if you do 8.1 days and you divide by one half-life of 2.7, you get 3 half-lives. So 3 half-lives have passed in 8.1 days. So then what you do is simple. You start with your 96, which is your starting amount, and you split that in half 3 times. So after the first half-life, you have 48 grams. After the second half-life, you have 24 grams. And after the third half-life, you have 12 grams that remain. So again, every half-life problem is going to follow that pattern. So let's look at one more problem. A 208 gram of sodium-24 decays to 13 grams within 60 hours. What is the half-life of this radioactive isotope? So again, I have my knowns. I have sodium-24. I'm not going to use that 24 in my math, so don't get confused. My starting amount is 208 grams. My ending amount, that says 13 hours. That should say 13 grams. Sorry about that. And the time that has passed is 60 hours. So now let's look at this. We know that we started with 208 and then we ended with 13 grams. So all you have to do is start with your starting amount and you're going to half that until you get to 13. So we have 208 grams to 104 to 52 to 26 to 13. And that took 4 arrows, which means 4 half-lives. Then what you do, go back to your problem. 60 hours have passed. So in 60 hours, we have had 4 half-lives. All you do, 60 divided by 4, and you get a half-life of 15 hours. So every 15 hours, this sample is going to have a half-life, which means that half of its original amount has undergone nuclear decay. So I hope this has been helpful for you. I know half-lives are a struggle sometimes and it's difficult to understand them, but really if you follow that pattern, you can solve virtually any half-life problem. So this has been Science for Everyone with Tom Copeland. I'm Tom Copeland, and remember, science is for everyone.